Hello. What's yours?
Thanks. Good morning. My name is Ola Zawalna-Geer, and I am a research fellow at the University of Exeter. I'm working on replicability study. Unfortunately, I cannot see the screen for some reason on this laptop where the camera is, so I will be looking the other way. It's not that I'm rude, it's just I cannot see. Anyway. Today I'm going to present to you SWAC replicability requirements. I start to show the very simplified SWAC system diagram on the left here. So these are all components needed for the SWAC design. Also on the right, you can see how it can be optimized and what parts are needed into optimization. And here we have the technical requirements, which are obviously probably most important ones. Then we have the environmental studies and the financial analysis. But as we can see on this diagram as well, that they all overlapped each other, and in a very, very middle is the replicability, and the replicability will need all those parts to actually work and find the optimum SWAC design for the particular location. On the left here, we have the channel, and we have all of the eligible regions for the SWAC. Of course, we need location close to the coast, so some of those regions are totally not applicable, and we are not going to consider them at all. Jamie prepared here a very good map, and it's on the right, and it is with all location which we already identified for potential end users. So we can see that on all eligible areas, we have quite good density of potential end users. Those all end users were categorized because obviously the SWAC system will not work the same for every end user, because every end user will have the different requirements for the cooling. And of course, once you have the end user, you are doing it individually for them. But for this particular study, we had to categorize them to make some optimum for each. And we categorize them in many ways. So there are hospitals, there are hotels, there are aquariums, there are data centers, etc., etc. So first, I already mentioned that probably the most important part here for optimization are technical requirements. And we identified five main components for the optimization, and this will be optimized as an object-orientated optimization. And here we have intake depth. It's obviously very, very important, because based on the intake depth, we will have the different components will depend, like intake length and head loss as well. Then we have the heat exchange area, and I called it here heat exchange area, but really we are looking at the heat exchangers. And talking about the heat exchangers, we are looking at the position of heat exchanger, number of heat exchangers, maximal flow for each heat exchangers, also automatic filters, how many, where, size, etc., but also how much heat is being exchanged. And here we have, I assumed above or equal 0.5. We are for optimization doing 0.5. And this is because we cannot reach very cold water in the channel, and this is probably our optimum. Then we have the SWAC maximum thermal power. So obviously, for each individual site, it will be SWAC will have the optimal power, and we are in the first phase. We're looking at the two scenarios. So one is with the chillers, and then is with the SWAC, and based on it, we can calculate the best, the maximum thermal power. And it will depend on a few things. First of all, it is maximal customer cooling need, then what's the targeted delivered temperature, and few more, as we can see. Then having the thermal power, we can calculate the cooling power, and based on the cooling power, we can calculate the expected flow rate. Expected flow rate, it is needed to establish or optimize the pipe diameter. It's very important to know what diameter it is, because flow rate will relate to heat exchangers, pumping system, the length, etc., and the biofouling as well, to prevent biofouling. And then we have pumping system. So again, we are here looking at if it is already pumping system, because many sites may have already air conditioning cooling systems. So it can be something already existing, which we will try to adopt for the SWAC system, or we will start from the scratch. So again, pumping system, it will be location, if it will be over or under the water, the type, capacity, those kind of things. Then environmental requirements are obviously very important as well. And here we identify three main, and it's local bathymetry, because on the bathymetry, we will look into the optimal intake depth, optimal intake length, but also how to install all of the geometry of the bottom of the channel where it would be installed. Then the thermal gradient of the seawater, it's needed for estimation of the cooling power available for individual SWAC, but also we are looking at the surface air temperature. So this is another very important parameter. So these are three most important, but of course we have to look at other things as well. And other things are more like on the traffic light system. So if it is something feasible, and it's definitely yes, we will go for it. But if it's not, we will look if we can optimize it, if it can be improved. If not, we can just totally ditch the idea. If it is improved, we have to see how much and how much it would cost. There are all the parameters as well, like constraint parameters will be thermal discharge and mixing zone, but they are very important for each SWAC system. We will have to look at environmental constraints. So we will have to look at the tides and currents, because it will be important for the installations. Then we will have to look at the mandatory regulations, but this is different tasks, so I will be just getting the information from there. And environmental impact assessment, again, this will be something what is already done, and I will be just gathering the information. So first thing I am doing, it is in the progress. I thought it would be a really good idea to create a map for the whole channel to see where the SWAC has potential. So we have all of the end users, but now we have to see how applicable SWAC system would be for them. We're starting with the three main things, and we are doing the maps of the seawater temperatures, and I'm doing the sea temperatures of 15, 10, and 5 degrees Celsius at a different depth. So starting from very close to the coastline, 0.5 meters, and going all the way to 50 meters, but they're very optimistic. I don't think we will go that deep, but just to check. At the end of the day, it's just a study. Then we're doing also topography of the shoreline. And here, again, maybe I am a little bit too optimistic, maximum 10 meters. But again, this is just a study. But also this shows why we cannot take all of the eligible regions into considerations, because it has to be close to the coastline to be efficient financially. And also bathymetry of the channel. This is very important because we need to see the geometry for the installation, but also to see how long, where's the intake depth, how long the pipes need to be. And all three components will go into the locations maps with temperatures 15, 10, and 5 degrees Celsius. And we will be looking, again, very optimistic, up to 1 kilometer from the shore, but it has to be efficient financially, so probably it will be less than 1 kilometer. Then this kind of information will go into another. This will be input for another component, like length of pipeline to reach depths with temperatures of 15, 10, and 5 degrees Celsius. And again, they will be shown as maps. In the meantime, I will be looking also at the hourly air temperature, and I will be looking at the temperature of 15, 20, 25 degrees. It may be hourly, but actually just looking at this Bruno's presentation today and him doing it by 3 hours, maybe I will change it to every 3 hours and it can be totally sufficient. Based on this information, I will be able to calculate the SWAC capacity factor and again make the maps. And this, as well as the length of the pipeline, will be input to compare the shortest pipeline with the capacity factors and the depth with the temperature less than 15 degrees Celsius. Having this information, I will be able to estimate the SWAC cost for the whole channel for all coastline. So this is the idea. This is the progress. The whole work is in the progress. I think it can be quite interesting, and I will be very happy to show it next time I'm presenting. And the last part of the replicability study will be multi-objective optimization. So in this case, we'll be optimizing how to make SWAC cost efficient, but also environmentally friendly. And of course, you cannot satisfy everybody. So we will find the different solution, and it will be multi-solution, and the potential future end user will be able to look into this optimization and choose where they want to be, what solution is best for their site. And to do so, this will be there is already code ready in MATLAB, but this is planned, not in progress yet. And here I already discussed it with Jamie. Jamie, can you take over?
Sure, yes. So my name is Jamie, and I'm based at the University of Exeter Business School, and I'm working on T4 as well as part of the market study and potential business models for the upscaling of the SWAC systems. As Ola's mentioned already, we've been working, Ensta's been leading the potential site studies for short-term replication sites within the project. And on top of Newham and Brixham, demonstration sites, 6 sites have been identified. 1 has confirmed they'd like to study on their site, and a further 4 have expressed their great interest and should soon confirm. And we also have 1 which we're waiting to hear by. We're aiming to have a definitive list validated by the end of June. And we're still always on the search for further replication sites in case some of those additional sites stay there. Thank you, Karen. Next slide.
Yeah. You go.
So I'll just there's a lot of information on the table there. So I'll give a brief summary as to how we are developing a potential future business model for the upscaling of SWAC. Starting with the columns up there, we are looking at various usage models and comparing against other scenarios. So the usage models we're looking at on the left-hand side is no SWAC, or traditional air conditioning system. And then in the centre there, we're looking at a SWAC system as we're modelling at the moment. Then on the right column, we're looking at a circular SWAC system. Now, to give a brief introduction, whether we make a SWAC system at the moment or in other sorts of similar process and engineering, may make also a linear model, as you take from the environment, reduce a SWAC system, for example, then in this life cycle, we may dispose it and throw it away. The circular SWAC system on the right-hand side of this table, we're going to have a look at the usage model where we produce a SWAC system, and at the end of its life cycle, we don't throw it away, we regenerate it, refurbish it, and we can try and use it elsewhere. So those are the 3 usage models that we're looking at. And we're also looking at 2 separate scenarios down the left-hand side, where we're looking at the optimized model, which Ola is working on. And then on the bottom scenario, we're looking at alternative materials. We may swap out a couple of materials in the SWAC system in order for more durable alternatives, in order to further extend the life cycle. So basically battling against the short terms and which you may encounter in engineering, and seeing how we can again extend that life cycle. And in the way that we're modelling these, we're using 3 separate methodologies. And we are measuring the environmental impact, the economic cost, and the social impact of each of those 3 models against both scenarios. So with the top scenario, I'll briefly summarise. With no SWAC, we might move from an altered environmental impact and a standard economic costing on a traditional air conditioning unit with little social impact, moving through a SWAC system which we're optimising at the moment, where it anticipates an improved environmental impact and optimised economic terms through capital expenditure and operating expenditure, and social benefits drawn through improved quality of life and creation of jobs. But if we get to a circular SWAC system, again, we'll have all of those environmental and economic and social benefits on a traditional SWAC system, but enhanced through a reduced extraction of resources, because we don't need to take quite as much material to make a new SWAC system at the end of its service life. We're reducing costs through regeneration, and we're sustaining social benefit for expertise, labour, creation of jobs and upskilling up the supply chain, and awareness of sustainability, and even more improved quality of life. And then in the bottom scenario, again, if we use those same methodologies to move across the right side of the table, again, on the left-hand side, we might have an altered environmental impact. We might have an increased capital expenditure through the use of more durable or slightly more expensive materials, but again, you have a longer life cycle. You'd have a little social impact, of course, with the traditional air conditioning system. But then as we move across to the right, again, we start to see all those improve. So with a more durable material-based SWAC system, you have improved environmental impact and a further improvement for more durable material. Again, the financial terms of SWAC would be improved, and social benefits would be drawn through improved quality of life. And then with a circular SWAC system, with even more durable materials, again, you would be seeing more significant environmental improvements through reduced extraction of materials through reused or durable materials. There might be an initial capital expenditure increase, but you have a longer life cycle optimised through more durable materials. And again, you'd have the same sustained social benefit through upskilled labour, job creation, and improved quality of life. So hopefully that explains it, summarises it quite well. And from those 3 usage cycles, we'll then create a business model which we hope we can use to upscale SWAC in the future. Next slide, please, Ola. This is, so we've talked about, I've talked about the environmental, economic and social methodologies which are employed. This covers very briefly the economic life cycle costing. So we'll be deploying a life cycle costing methodology to assess the economic cost of air conditioning options within those scenarios there. Using it to work out capital expenditure and the operating expenditure, as well as maintenance and disposal, and in the case of the circular SWAC, regeneration cost. We've taken into account all those aspects down the right side of the diagram there. So I'm looking at maintenance, repair, the admin which may be required, as well as the discount rates of the future, any revenue that comes in. And what we'll be doing is comparing the economic cost of each scenario to generate a sort of a comparative payback period, which again tells us the most cost-efficient, cost-innovative usage model to develop a business model from. Thanks, Ola.
Okay, so yes, thank you very much. Any questions?